Electric vehicles, or EVs, are often celebrated as the clean, green future of transportation. They move almost silently, gliding through our cities and neighborhoods, leaving behind no tailpipe emissions and offering a driving experience that feels both futuristic and responsible. Their quiet operation and instant torque have made them a symbol of progress, efficient, innovative, and seemingly free from the pollution that plagues traditional gasoline cars. The promise of EVs is simple, yet powerful, a better, cleaner way to get around. This vision has sparked a global surge in electric car adoption, with millions of drivers making the switch in hopes of reducing their carbon footprint and contributing to a healthier planet. Governments and automakers alike are investing billions to accelerate this transition, building charging networks and rolling out new models at a rapid pace. But beneath these sleek exteriors and high-tech dashboards lies a hidden complexity that most drivers never see or think about. The secret to the impressive performance of electric cars? It's the powerful magnets made from rare earth elements, tucked deep inside the electric motor. These magnets are the unsung heroes, enabling the instant acceleration and high efficiency that drivers have come to expect from modern EVs. Without these rare earth magnets, electric motors would be bulkier, less efficient, and far less powerful. They are absolutely essential for delivering the range, speed, and reliability that make EVs so appealing. Yet, sourcing these critical materials is anything but clean. The process of extracting rare earth elements from the earth is energy-intensive and often leaves behind toxic waste, polluting water and soil in the regions where they are mined. The journey of an electric vehicle begins not in a factory, but in distant mines, sometimes in remote or politically unstable regions, where the supply chain is fraught with both environmental and ethical challenges. These include habitat destruction, hazardous working conditions, and even concerns about human rights abuses. This creates a troubling paradox. The very components that make electric cars so clean and desirable on the road are built from ingredients that can be dirty and damaging to the planet. It's a hidden cost that's rarely discussed in the excitement over EVs. This reality raises a crucial question for the future of transportation. Can we make electric cars truly clean, not just on the road, but all the way from the raw materials to the finished product? The auto industry has been searching for answers, but building high-performance motors without rare earths has proven to be a major engineering challenge. Alternatives exist, but they often come with trade-offs in size, weight, or efficiency. Rethinking motor design to maintain the power and efficiency drivers expect, without relying on these problematic materials, has become the next great frontier in automotive engineering. It's a race to innovate, to find solutions that are both sustainable and practical. The search for a truly clean solution is now reshaping the future of sustainable transport, pushing the industry to balance performance, ethics, and environmental responsibility like never before. Rare earth elements aren't actually rare, despite what their name suggests. In fact, they're found all over the Earth's crust, scattered in small amounts across many types of rock and soil. The real challenge is that they're rarely found in high enough concentrations to make mining them easy or economical. Extracting just a few grams often requires moving and processing tons of earth. This process is not only expensive, but also comes with significant environmental costs. Mining rare earths can lead to toxic waste, water pollution, and habitat destruction, making their extraction a controversial topic worldwide. Yet their unique magnetic properties make them incredibly valuable. Neodymium, in particular, stands out. When it's combined with iron and boron, it forms neodymium magnets, the strongest permanent magnets known to science. These powerful magnets are at the core of the most advanced and efficient electric motors. They allow motors to deliver high torque and impressive acceleration, while keeping the motor itself compact and lightweight. For electric vehicle owners, this translates to more miles per charge, faster acceleration, and less range anxiety on long trips. It's a key reason why modern EVs can compete with and often outperform traditional gasoline cars. Permanent magnet synchronous motors, or PMSMs, have become the gold standard in the EV industry because of these advantages. Their efficiency and power density are unmatched by most alternatives. In these motors, the neodymium magnets are fixed to the rotor. When electric currents flow through the stator, they create a rotating magnetic field that interacts with the magnets, causing the rotor and the wheels to spin smoothly and efficiently. The strength of these magnets is crucial. It allows for smaller, lighter motors that don't sacrifice performance, making them ideal for electric vehicles where space and weight are at a premium. However, this heavy reliance on rare earths comes at a significant cost, not just financially, but also in terms of environmental impact and global supply chain risks. Most rare earths are mined and processed in just a few countries, leading to geopolitical tensions and supply vulnerabilities. For years, the industry has accepted this trade-off, believing that rare earths were essential for top-tier EV performance and efficiency. The benefits seem to outweigh the drawbacks. But now, with growing concerns about sustainability and supply security, that long-held assumption is being challenged. Automakers and engineers are searching for new solutions that could reshape the future of electric mobility. Mining rare earths is an environmental minefield, fraught with challenges that extend beyond the immediate extraction process. Open-pit mining scars landscapes and destroys habitats, all for tiny amounts of usable material. The visual impact is stark, leaving behind barren lands that struggle to recover. The process generates massive waste, tailings that can be toxic or even radioactive. These waste products pose long-term environmental hazards, seeping into soil and water systems. Refining rare earths involves hazardous chemicals, producing toxic wastewater and polluting air and water. The chemical runoff can devastate local ecosystems, affecting both wildlife and human communities. Most of the world's rare earths are processed in China, creating a risky global dependency. This centralization of processing facilities means that any disruption can have worldwide repercussions. This concentration gives China immense market control, leading to price swings and supply chain vulnerabilities. The geopolitical implications are significant, affecting global trade dynamics. Automakers face unpredictable costs and potential disruptions, complicating production and pricing. The reliance on rare earths makes the automotive industry particularly vulnerable to these fluctuations. The high price of rare earth magnets inflates EV costs for consumers. This cost is often passed down to buyers, making electric vehicles less accessible to the average consumer. The industry has long sought to break free from this costly, risky dependency. Researchers are exploring innovative solutions, aiming to find sustainable alternatives that can reduce reliance on rare earths. The environmental and geopolitical stakes are high. As the demand for clean energy grows, so does the urgency to address these challenges. The search for alternatives is more urgent than ever. Scientists are working tirelessly to develop new materials and technologies that could revolutionize the industry. The future of EVs may depend on it. As we move towards a more sustainable future, finding solutions to these challenges is crucial for the continued growth of the electric vehicle market. In March 2023, Tesla made a game-changing announcement. Its next-generation electric motor would be free of rare earth elements. This wasn't a minor tweak, it was a fundamental shift in motor design. Tesla's move sent shockwaves through the industry, signaling that high-performance EVs could be built without rare earths. The goal? Lower costs, and a more sustainable, secure supply chain. This innovation is central to Tesla's Master Plan 3, aiming for mass production without rare earth constraints. Tesla promised no compromise on performance or efficiency. The timing was crucial, as global supply chains faced mounting pressures and rare earth prices soared. Tesla's bold step was about future-proofing its business and leading the industry toward true sustainability. The message was clear: the era of rare earth dependency in EVs could be ending. So, how does Tesla's new motor work without rare earth magnets? The answer: a reluctance motor, likely a switched or synchronous reluctance design. Instead of magnets, it uses shaped steel rotors and precise control of electromagnets in the stator. The stator's electromagnets pull on the rotor's teeth, spinning it by rapidly switching currents in sequence. Advanced software and power electronics are key, orchestrating this process with perfect timing. The result? A rugged, simple, and cheaper motor, no rare earths required. Historically, reluctance motors were noisier and less power-dense, but Tesla's software breakthroughs have minimized these downsides. The new design delivers smooth, quiet, and powerful performance. It's a leap in both engineering and sustainability. Tesla's innovation could redefine what's possible in EV motor technology. Tesla's motor evolution tells the story of the industry's search for the perfect balance. Early Teslas used AC induction motors, no magnets but less efficient at low speeds. The Model 3 introduced permanent magnet motors, boosting efficiency and range. Dual motor setups combined both types for optimal performance. Now, the rare earth-free reluctance motor aims to match PMSM efficiency without the supply chain risks. This requires advances in design, materials, and especially software. Other automakers have tried alternatives like Renault's copper-wound rotors and Maele's magnet-free motors, but with trade-offs. Tesla's bet on reluctance motors is a bold new path. If perfected, it could offer simplicity, lower cost, and high performance. The race to build the best magnet-free motor is on. The biggest win from rare earth-free motors? Lower costs. Rare earth magnets are expensive and volatile in price, eliminating them slashes motor costs. Manufacturing is simpler, just steel laminations, no delicate magnets. This means faster assembly, fewer defects, and billions saved at scale. Environmentally, it's a leap forward. No more dirty mining or toxic refining in the supply chain. Tesla's move strengthens its green credentials and appeals to eco-conscious buyers. It also stabilizes the supply chain, relying on abundant, predictable materials like steel and copper. The result, cheaper, greener, and more resilient EVs. Tesla's shift has forced the entire auto industry to rethink its approach. Legacy automakers and startups alike are now racing to develop their own magnet-free motors. Companies like Renault and Mahle are accelerating their efforts, spurred by Tesla's bold move. This wave of innovation will drive down costs and improve technology for everyone. Reduced demand for rare earths could reshape global markets and supply chains. Tesla's decision is a catalyst, pushing the industry toward a more sustainable, resilient future. The era of rare earth dominance in EVs may be coming to an end. Tesla's rare earth-free motor marks a turning point for electric vehicles. It addresses cost, sustainability, and supply chain risk in one stroke. Lower motor costs bring EVs closer to price parity with gasoline cars, accelerating adoption. The focus on software-driven motors signals a future where cars improve over time. This innovation will spur further breakthroughs in power electronics and control systems. As the technology matures, EVs will become cheaper, cleaner, and more accessible. Tesla's move sets a new benchmark for the industry. The silent hum of this new motor could be the sound of the next great leap in automotive history.